Welcome everybody to our calculus notes for section 1.1. Today we're going to be looking at a preview of calculus. So what is calculus? Calculus is the mathematics of change, and more specifically it's the reformulation of a pre-calculus math through the use of a limit process. So chapter 1 is going to be all about finding limits, and then we're going to apply this to calculus. So a fundamental principle is that you can use approximations of increasing accuracy to find an exact answer. So we're going to look at approximations getting closer and closer to narrow in on an exact answer. So an example is estimate the distance on the curve of f of x equals x squared from the point 0, 0 to 416, and we're going to do this using 2 points, then 3 points, and then 5 points. So here's what we're trying to do. We're trying to find the distance from 0, 0 along the curve of f of x equals x squared up to the point 4, 16. So we want to find that length. Well, we can start off just by looking at 2 points. So going from 0 to 0 to 416, and if we look at 2 points, we would have this line right here. And we can find the length of a line, and that's just using our distance formula. So we would get the square root of 4 minus 0 squared plus 16 minus 0 squared. And if we plug this into our calculator, we get about 16.49. So that's a very rough estimate of the length of the curve. Let's go ahead and try this now with 3 points. So what we're going to do is we're going to add a third point somewhere here in the middle. So in between x equals 0 and x equals 4, we'll add the point 2. And we know this is x squared, so this is going to give me the point 2, 4 here. So now what we can do is actually split this up into 2 line segments, from here and then from here to here. And you can see already that this red line is more closely approximating our curve. So let's go ahead and find these 2 lengths now. So the first one is going to be the square root of 2 minus 0 squared, and then plus 4 minus 0 squared, and then plus the second line segment from 2, 4 to 416. So that's going to be 4 minus 2 squared plus 16 minus 4 squared. All right, and you can use a calculator here to solve this, or we can just evaluate it on our own here. So this is going to be 2 squared, which is 4, and 4 squared, which is 16. So that line segment is root 20. And then over here, this is going to be 2 squared, which is 4, and then 12 squared, which is 144. And the square root here is the square root of 148. And if we just approximate this in our calculator, we get about 16.64. So you can see we're getting a little bit closer, and we're narrowing down our approximations. Well, what if we added now 5 points? So what we can do is just split the difference between 0 and 2, and we'll look at the point here, and that'll be 1, 1. We'll still have our 2, 4. And then we'll go 3, 9, which is about right here. And then we'll still use the point 416. All right, so now we can see here are our line segments, purple. And you can see that this is getting a lot closer to the actual curve. So now we have 5 points and actually 4 line segments to find. So we have this one, the one here, the one here, and the one here. Okay, so our first line segment will be the square root of 1 minus 0 squared plus 1 minus 0 squared. And then between 1, 1 and 2, 4 will be the square root of 2 minus 1 squared plus 4 minus 1 squared. Between 2, 4 and 3, 9, we get 3 minus 2 squared plus 9 minus 4 squared. And then between 3, 9 and 416, we get the square root of 4 minus 3 squared plus 16 minus 9 squared. All right, and so this will give us 1 squared plus 1 squared, so that's root 2. Then over here, this will give us 1, and this is going to give us 3 squared or 9, so we actually have square root of 10. Over here, we get 1 plus 5 squared or 25, so this is actually root 26. And over here we'll have 1 plus 7 squared, which is 49, so we actually have root 50 here. All right, and if we go ahead and add all of these up into our calculator, we'll get an approximation of about 16.75. And it makes sense if we look at these that they're getting a little bit longer each time, because the shortest distance between 2 points here is that straight line. And so as we get closer to the curve, this approximation is going to get a little bit larger. And we're going to be able to do this a little bit later on in the year using calculus. And calculus actually gives us an answer of 16.8186. So you can see that we're getting closer, but here's the key. If you increase the number of points, then you also increase the accuracy. So what calculus does is let the number of points go to infinity. So if we had an infinite amount of points on this curve and we added up all the line segments, well, we would get a very close approximation. And the limit process is going to end up helping us to do this. So there's two branches of calculus. The first one we're going to talk about is differential calculus, and the second one is integral calculus. So all semester 1 will be differential calculus, and all semester 2 is mostly integral calculus. So differential calculus takes the idea of a secant line becoming a tangent line. So a secant line is a straight line that intersects a curve in 2 points. So if we just take any curve here, our secant line will intersect that curve in 2 points, here and here. Now we can actually find the slope between these 2 points. We could call this x sub 1, y sub 1. We would call this x sub 2, y sub 2. And remember that our slope would be rise over run. So it would be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay, so we could actually find the slope of our secant line there. Now, a tangent line is a straight line that just touches a curve at a single point. And the slope of the tangent line and the function at that point are equal. So we can say that a slope of any function is equal to its tangent line at that point. So let's draw that same curve, and then let's go ahead and make a tangent line to the curve right at this point. And so what that means is it's a line that comes and just touches at that one point and keeps on going. And what we're going to say here is the slope of the line and the slope of the curve are the same right at this point. So let's take a look at the tangent line problem. So we can actually use our Desmos app here to kind of explore this concept of finding the slope of a tangent line. So if we open up our Desmos app, and then on the left-hand side, click on the 3 lines, and then choose Calculus, and choose Secant line, and then explore this graph. So what we have here in blue, we have f of x equals sine of x plus 0.3x. And then in red, we have y equals m times x minus a plus f of a. And that's really the equation of a line through the 2 points, a f of a, which is right there, and a plus h, comma, f of a plus h. So let's zoom in a little bit here. And let's just say that we want to find the slope of the line at x equals 1. So we want to find the slope of the blue line right here. So what we can do is take this secant line and actually move the other point closer, and eventually we're going to get a really good approximation of the slope of the tangent line as this gets closer and closer to our point. So now you can see that the slope of the red line is very close to the slope of the blue line. So we can see here in number 4 that that is our f of a plus h minus f of a over h. And in your notes, it's f of c plus delta x minus f of c over delta x. It says the slope of the secant line through points P and Q as Q approaches point P nearly equals the slope of the tangent line through point P. So using the slope formula for m, y2 minus y1 over x2 minus x1, find the slope of the secant line through the points P, which is c comma f of c, and Q, which is going to be c plus delta x comma f of c plus delta x. All right, so let's make our drawing here. So let's draw a little curve right here, and let's go ahead and put the points P and Q on it. So we'll just say here is P, and here is Q. And so P is the point C comma f of c. So this is our c value, and then the height is going to be f of c. And then for Q, Q is going to be c plus delta x comma f of c plus delta x. And that actually maps down here to where this is c plus delta x, and then this y value is f of c plus delta x. And you can see here that delta x is just the difference between these 2 points. And so let's go ahead and find the slope of the secant line through those 2 points. Okay, so the slope of our secant line is going to equal y2 minus y1, so that's f of c plus delta x minus f of c over x2 minus x1. Well, x2 is c plus delta x, and then x1 is just c. And you can see if we simplify now that c minus c drops out, and so we really have the slope of a secant line is going to be f of c plus delta x minus f of c over delta x. Now as delta x shrinks, the 2 points get closer, and the limit as x approaches 0 gives us the slope of the tangent line. So what we've really formulated here is something called the difference quotient. And this is something that you worked with in pre-calculus. And what the difference quotient is the slope of a secant line through 2 points. So our next example, we want to estimate the slope of the tangent line to the graph of f of x equals x squared at the point 1, comma 1. And we're going to use the following points for Q. So here we have 1, comma 1, and we want to estimate the slope of the tangent line at this point right here. Okay, so what is the slope of this line right here? First, let's find the slope of the secant line from the point 1.1 to 1.5, comma f of 1.5. So here's Q1. So if we want to find the slope, it's going to be f of 1.5 minus f of 1 over 1.5 minus 1. You notice here that this is the x value for Q1, and this is the x value for Q2, and here's the x value of the point that we're trying to find the slope of the tangent line for. So f of 1.5 is going to be 1.5 squared, and then f of 1 is going to be 1 squared, and then 1.5 minus 1 is really 0.5. And in our calculator, this is going to give us a slope of 2.5. Well, let's go ahead and get a little bit closer. Let's move Q to x equals 1.1. So now 1.1 and f of 1.1 is going to be somewhere about right here. So now Q2. And we can see here that the slope of this line is getting closer to that tangent line. So finding this slope, we want f of 1.1 minus f of 1 over 1.1 minus 1. And solving this, we get 1.1 squared minus 1 squared over 0.1. And when you plug this into your calculator, you get about 2.1. And let's even get a little bit closer. Let's find Q3. It's 1.01. And that was Q2. And now you can see that this line is getting really close. Now we're only 1/100th away, so delta x is 0.01. So if we want to find our slope, we would do f of 1.01 minus f of 1 over 1.01 minus 1. Notice that delta x is 0.01, and we have 1.01 squared minus 1 squared, and this gives us about 2.01. And we can get even closer. We can go within 1,000th away from our point 1, 1. So now we want f of 1.001 minus f of 1 over, well, the difference, 1.001 minus 1. And so we get 1.001 squared minus 1 squared over 0.001. And now when we plug this into our calculator, we get 2.001. So as delta x approaches 0, okay, and notice that delta x here is getting closer to 0, our approximation is getting better for the actual slope of the tangent line. So what do you think the actual slope of that tangent line is? Well, it looks like the measure of the slope of the tangent is going to equal 2 based on our approximations. All right, so that is the basics of differential calculus.